Finding second largest element in sliding window. Thought for a second. Here is your same structured beginner-friendly content for finding second largest element in sliding window, intermediate advanced level, window statistics, and ordered data structures. In sliding window problems, we often calculate values like sum, minimum, maximum. But sometimes we need more advanced information, such as second largest element, second smallest element, top k elements in each window. One important variation is find the second largest element in every sliding window of size k. This problem is more challenging than finding the maximum because we must track not only the largest element, but also the next largest one. It is useful for learning sliding window techniques, ordered data structures handling duplicates, efficient window updates. This type of problem appears in coding interviews, competitive programming, streaming data analysis, ranking-based window problems. Understanding this problem helps learners move from basic sliding window to advanced window statistics problems. Problem statement. Given an integer array, ARR, a window size k. For every contiguous subarray of size k, find the second largest element. Example, ARR equals 1, 3, 2, 5, 4, 6. K equals 3. Windows 1, 3, 2 means second largest equals 2. 3, 2, 5 means second largest equals 3. 2, 5, 4 means second largest equals 4. 5, 4, 6 means second largest equals 5. Output 2, 3, 4, 5. What does second largest mean? The second largest element is the element that comes just below the maximum in sorted order. In simple terms, second largest equals the next biggest value after the largest one. Example concept. 1, 3, 2 means sorted equals 1, 2, 3, means second largest equals 2. Important note about duplicates. We must be clear whether second largest distinct element is required or second largest by position order is allowed. In most algorithm problems, second largest distinct element is expected. Example 4, 4, 2. If using distinct values, largest equals 4, second largest equals 2. If second largest distinct value does not exist, we may return -1 null or follow the problem's requirement. In this explanation, we will assume we need the second largest distinct element in each window. Why? This problem is harder than sliding maximum. Finding the maximum is easier because we only care about the top value. But for the second largest, when the window changes, the old maximum may leave a new value may enter. Duplicates may affect the answer. We need the top two distinct values. Example concept. Need more than max means must maintain order inside window. So this problem usually requires a stronger data structure. Brute force approach. For each window, copy the k elements, find the largest and second largest, store result. Example workflow window means scan all k elements, means compute largest plus second largest. There are about n-k plus 1 windows. For each window, scanning k elements gives O(n) times k. This works for small inputs, but becomes slow for large arrays. Better approach, use ordered map, TreeMap. A more efficient solution is to maintain the current window in sorted order. In Java, a good choice is TreeMap integer, integer. This helps us insert elements, remove outgoing elements, get the largest key, get the next lower key, second largest distinct. Example concept. TreeMap means keeps window elements sorted automatically. Why TreeMap works well? TreeMap stores keys in sorted order. We also store frequency counts because duplicate values may appear in the window. Example. Value means frequency. For a window like 3, 5, 5, 2. Map becomes 2 means 1, 3 means 1, 5 means 2. Largest distinct value equals 5. Second largest distinct value equals 3. Sliding window logic. For each window, add the new incoming element, remove the outgoing element. Ask the ordered structure for largest value, second largest distinct value. Example concept. Add new means remove old, means read top two values. TreeMap-based workflow. Initialize first window. Get largest and second largest. Slide window by 1. Insert incoming element. Remove outgoing element. Get new second largest Java solution. Using TreeMap, import java.util. Public class, second largest in sliding window. Public, static, list integer, second largest in Windows. Int array array, int k. List integer result is new array list. If r equals null, or r length equals 0, or k greater than 2, or k greater than r length. TreeMap integer. Map equals new TreeMap. Build first window. For int I equals 0, I map plus. Map.put arin, map get or default arin 0. Process first window result. Add get second largest distinct map. Slide the window for int I equals k. I equals r length. Int outgoing equals ri minus k. Int incoming equals ri. Remove outgoing element. Map.put outgoing, map.get outgoing minus 1. If map.get outgoing is 0, map.remove outgoing. Dash add incoming element map. Put incoming, map get or default incoming, 0, plus 1. Result.add get second largest distinct map. Return result. Private static int. Get second largest distinct. TreeMap integer map. Integer largest is map.last key. Integer second largest is map.lower key largest. Return second largest equals null. Minus 1. Second largest. Public static void main string error args. Int error equals 132546. Int k equals 3. List integer result equals second largest in Windows rk. System.out.println result /2345. How the code works. Step 1. Build first window. 4. R equals 132546. K equals 3. First window is 1, 3, 2. TreeMap stores. 1 means 1. 2 means 1. 3 means 1. Largest equals 3. Second largest distinct equals 2. Step 2. Slide the window. Move from 1, 3, 2. 3, 2, 5. Operations. Remove 1, add 5. Now TreeMap stores. 2 means 1, 3 means 1, 5 means 1. Largest equals 5. Second largest equals 3. Step 3. Continue for all windows. The process repeats until the end of the array. Why lower key is useful. TreeMap.lowerKey(x) gives the greatest key strictly smaller than x. So, last key gives largest distinct value. Lower key, last key, gives second largest distinct value. Example concept. Largest equals map last key. Second equals map lower key. This makes the solution clean and efficient. Example with duplicates. Let r equals 4, 4, 2, 3, k equals 3. Windows. Window 1, 4, 4, 2. Distinct values. 4, 2. Second largest distinct equals 2. Window 2, 4, 2, 3. Distinct values. 4, 3, 2. Second largest distinct equals 3. Output. 2, 3. What if no second largest exists? Example. 5, 5, 5. Distinct values. Only 5. So, second largest distinct value does not exist. In our solution, we return -1. You can change this depending on problem requirements. Time complexity. Each window operation involves one insertion into TreeMap, one deletion from TreeMap, one lookup for largest and second largest. Each TreeMap operation takes O of log k. For all windows, O n log k. This is much better than brute force O(n) times k for large input sizes. Space complexity. The TreeMap stores at most the distinct values inside one window. So, space complexity is OK. Alternative approaches. This problem can also be solved using balanced BST/multiset max heap with lazy deletion, ordered frequency map, custom monotonic structures for special cases. But in Java, TreeMap is one of the simplest and most practical solutions. Example concept. TreeMap means easiest clean approach in Java, why DQ is not enough here. For sliding window maximum or minimum, DQ works very well. But for second largest, DQ alone is not enough because we need top two distinct values. Outgoing elements can change ordering in complex ways. Duplicates complicate direct DQ logic. Example concept. Maximum only means DQ works. Second largest means need richer ordering structure. Common mistakes: ignoring duplicates. Do not assume all values are different. Confusing second largest with second distinct largest. These are not always the same. Forgetting to remove window elements properly. If outgoing frequency becomes 0, remove it from the map. Not handling invalid cases. For example, k int 2 empty array k equals error.length. Example concept. Correct window maintenance is very important. Concepts learned from this problem. Understanding this problem helps learners understand advanced sliding window problems, ordered map usage, handling duplicates with frequency counts, top two element tracking in dynamic windows, efficient window statistics computation. This is an excellent problem for learning window-based order statistics. Simple definition. Finding second largest element in sliding window. For every window of size k, find the second largest distinct element efficiently as the window moves. Final summary. The problem of finding the second largest element in every sliding window is more advanced than basic sliding window maximum or minimum. A brute force method checks each window separately, but that is slow. A better solution uses a tree map with frequencies to maintain the current window in sorted order. This allows us to efficiently get the largest distinct value, the second largest distinct value. The overall time complexity becomes O(n) log k, which is efficient for large inputs. Understanding this problem is important for mastering advanced sliding window techniques, ordered data structures, and dynamic ranking problems.